Now, if you see here, every time I had world-class presentations, okay, and I still have the world-class presentation, but this non-normal distributions, all of you type NND in the chat box. Non-normal distribution. All of you type non-normal distribution. We all know about normal distribution, the bell-shaped curve, okay, which is symmetric towards the end, and the whole world talks about normal distributions. But when I talk about non-normal distribution, it's going to be really interesting for those people who wanted to explore this further, but the applications are quite limited. Okay, normal distribution application is quite common. But then I'm going to give you an exhaustive list of non-normal distributions and pick up almost a few of them, which is quite used, and tell you some practical applications of this. How many of you are excited to learn? Type XTD, XTL in the chat box. Excited to learn. How many of you are excited to learn? Let's see. How many of you are excited to learn? And the way that I'm going to share today is going to be something totally different. All right, good. A lot of people who are excited to learn. Thank you very much for this. Let's see here. Okay, so what do you see on the screen? Type in the chat box. What do you see on the screen? Okay, if you see non-normal distribution, type N and D in the chat box if you see, so that I want to make sure that you see the right screen. And this is chapter 20. Okay, this is chapter 20. All right. So I'm going to share with you 3 types of non-normal distribution: continuous, discrete, and multivariate. Okay, all of you type CDM in the chat box. CDM means continuous normal distribution, discrete non-normal distribution, and okay, CMD is also fine. Okay, CMD, like chairman and managing director. If you want to associate and learn like that, CMD is also fine. DCM is also okay. Good, whichever way that you can understand. Okay, continuous, discrete, and multivariate. Okay, fine. Thank you very much. Now, if you see here, continuous, there are various continuous non-normal distributions here. Exponential, log normal, and variable. All of you type ELW in the chat box. Exponential, log normal, and variable. EWL in the chat box. This is quite commonly used to the first 3 non-normal distribution. Okay, fine. Thank you very much. Now, exponential distribution, if you see, time between events, the time to failure. I'll share with you the example of this. Log normal, if you see, the case study is stock prices, income, these examples from the log normal distribution. It's a skewed data, positive values only. Variable is used for reliability analysis. Okay. Now, this is going to be little, since nobody teaches this, okay? No one in the world teaches all these distributions in Six Sigma, okay? But I want my community members to be, I'm going to share with you the entire PDF of all this today, okay? So Cauchy distribution is used in physics and resonance. Logistic distribution is S-shaped type of distribution, which is used in logistic regressions and growth models. Laplace, it's actually a double exponential sharp peak, which is used in signal processing. Uniform distributions, where all the values are equally likely, is random generation number stuff. We are going to talk about that. And beta distribution is used in modeling probabilities. Gamma distribution is used in insurance claims. Triangle distribution is going to use in project management. Pareto distribution will be used in wealth distribution. Rayleigh distribution is going to be used in signal processing. Gumbel distribution is going to be used in the rainfall and stuff like that. If you are actually excited about this type, wow in the chat box, WOW, wow in the chat box. My request to you is don't get overwhelmed. Don't get, oh my God, how will I learn all this? Don't look at this, okay? Just put it in your mind. When the practical application comes, refer back and say, hey, I learned from, because all the distributions are not applicable across all industries. So whenever you encounter the real world scenario, you at least recall that, hey, I learned from Dr. Murli something like this. If it is reliability analysis, hey, I learned it. Which reliability analysis? Dr. Murli told me which distribution is that. Oh, it's a variable distribution. Let me go and look at what is variable distribution. Okay. If you found this is interesting, useful, fantastic, valuable, whatever it is, just put in the chat box. I'll feel happy that I've shared something useful to you. Okay. Now, discrete distribution. Okay. Discrete distribution. Good, fantastic. Yes, you will get the recording of the lessons and all that. Let's focus on the subject here. I will share all that inside the group. Okay. All right. Now, discrete non-normal distributions are binomial, Poisson, and geometric. These are the three major. Top three I've put here, all of BPG. Okay. All of you type BPG in the chat box. If you remember top three, it is enough. Okay, binomial, Poisson, and geometric distribution. So quickly, binomial is number of successes in fixed trials. It is widely used. Defectives in a batch. Okay, all of us have defectives. Okay, and Poisson is used the number of calls per hour. It's used in BPO very widely. And geometric distributions, if you see, the time to get first defect. I'm going to share with you the practical case studies of application in each and every one of them. Okay, and negative binomial is again reliability testing like we have seen earlier, and Bernoulli is coin tossing. Bernoulli's theorem we know, and hypergeometric and multinomial. These are not is very deeper in research. Okay, so discrete non-normal distributions. Last but not the least, you have multivariate or other specialized distributions like Dirichlet, multivariate T, and chi-squared. Chi-squared is widely used. I'll put chi-squared on the top, multivariate in the next. Okay, I'll also highlight chi-squared. Okay, chi-squared is what we use in hypothesis testing, and multivariate we use in robust modeling. And for example, in AI, they are using multivariate models. Okay, and multivariate generalization of beta is probabilities of multiple categories. Okay, these things, don't worry about that. It's not applicable across. But at least I want you to understand that, okay, all these stuff is here. Okay, all such stuff is here. All right, now let us go into the detail of this. Let us go into the practical case studies of some of this. Okay, now, if you're ready, just type ready in the chat box. I want excitement from you because all these examples, some might be relevant to you, some might not be relevant to you. But be patient, be focused, make sure that you absorb the content like a sponge. Okay, absorb the content like a sponge and go out and research in the world of Googles and Chat GPTs and Geminis to make sure that you expand your knowledge to the next level. I want to be your source of inspiration to explore further. Okay, I cannot share everything with you. It is not possible for you to understand everything, but I want you to be the source of inspiration. Let us get into the continuous non-normal distributions. We have already said that exponential distribution is time to failure. Let us take some practical examples. Okay. So exponential distribution, if you see here, the practical day-to-day exponential distribution is this. Waiting time between customer arrivals. Okay. Customer A comes, then customer B comes. Okay. And even in the mall counter, you wait, right? So even the ATM, for example, let's say ATM or the bank queue. How long will I wait before the next customer arrives? Okay, so this distribution is random, independent. What is random, what is independent, and all that stuff we have already taught. Okay, but the practical example of exponential distribution is waiting at ATM for queue. So assume that on average 10 customers arrive in the ATM per hour. So there is a formula here. So one customer every 6 months, and you can apply this formula. I'm not going to go into the depth of this, but I'm going to show the highlight of it. And the other real world, it can be used in examples like this, the customer waiting times, and real world uses. You can take this, for example, time until the light bulb burns out, time calls between calls in the call center, time until the next order on the e-commerce site, time between earthquakes and system failure. Okay, so if this example is clear to some extent, at least give me a 9 or 10 if you have understood this example. I cannot go into the depth of each and every example, but I can give you the overview of some of that. Okay, good. Thank you. If you understand exponential distribution, I'm very happy to do this. Thank you very much. Okay, let me quickly get into the next because we have another 20 minutes. Let me try to cover as many distributions as possible. We already seen that it's a skewed data, positive only, stock prices and income. Okay, let me open up the examples here. What here? Okay, modeling household income distribution. This is the example of a log normal distribution. Okay, modeling household income distribution. Why? This is income is strictly positive. All of us know there is nothing called as negative income. A small number of people earn high incomes, causing positive cues. Okay, most people earn income around lower mode or median, but not average. Okay, if this is clear, type SC, super clear in the chat box. So practical uses is governments and economists use log normal distributions. What do they do for? To estimate income inequality, plan the taxation policies, allocate subsidies, and marketers use it for segment customers based on purchasing power, set up product pricing for different income groups, etc. Okay, and another example I would like to give here is a city council is designing tiered utility pricing system. They model household incomes using log normal distribution. This helps them identify income brackets. Okay, as a result, they charge lower rates for lower income families and higher rate for higher income families. Okay, fine. So if this was useful, this example was useful, just type useful in the chat box. Okay, this is an example of a log normal distribution. Now let me go into the variable distribution. Variable distribution, we said mostly reliability analysis. It's time to failure modeling. Variable distribution. Fantastic. Okay. Variable distribution. Okay. Thank you very much, each and every one of you who said this was useful. Okay. Let me share with you the application. Variable distribution is predicting appliance failures. Okay. All of us have washing machines. Okay. And imagine you are managing a home appliance warranty service, or you are the customer who bought a washing machine. The scenario is this. You want to understand when most washing machines tend to fail after purchase. Okay. So that you can plan warranty periods, offer extended warranties, and optimize your spare parts inventory. That's the scenario. So how variable distribution helps is variable distribution is ideal for time to failure modeling. Okay. It handles increasing failure rates, that is the wear out, constant failure rates, which is random, and even decreasing failure rates, okay, like infant mortality. So practical breakdown, if you see time period, failure pattern, variable distribution, variable shape parameter, which is beta, real world, okay, all this is something that you can learn further when you apply this distribution. And the insight for action you can do that is offer 2-year warranty or 3-year warranty or 1-year warranty. Maintenance plan you can recommend for 3 years or 4 years. I bought a AC, they gave a card for the compressor, some 5 years warranty card. Inventory planning and etc. Okay, and then industries, electronics, automotives, aviation, manufacturing, telecom, all that use this. Okay, if it was super interesting, type SI in the chat box. If you felt this was super interesting, I know for some people who is not used to all this, they might feel overwhelmed or even boring. But unfortunately, I need to share all this because I want you to become valuable. Okay. Now, let's talk about Cauchy distribution. You may not have heard about it, but let me quickly tell you. Thank you very much, each and every one of you. Okay. Real world example is resonance in electrical circuits. Okay. Radio audio system, when you tune your frequency, signal altitude response actually behave like a Cauchy distribution. Okay, practical scenario is as you move closer to the station's frequency, the signal gets stronger. But unlike normal distribution, the nearby frequency still produce a noticeable interference. Okay, due to heavy tells of the Cauchy distribution. Okay, why it matters is engineers designing filters, amplifiers might account this behavior to avoid interference. Okay. In optics spectrography, all this thing is used rather than normal distribution. Okay, so I will share this with you. Don't worry about this. If you want, you can take the screenshot of this also. But I'm going to share with you this complete PDF, okay, so that you can refer to it later. So that is Cauchy distribution, then logistics distribution. Okay, logistics distribution, yes model, other thing, logistic regression model. The practical case study is spam detection, email spam detection. Okay, the use case is classifying whether the email is spam or not a spam. Why do you use logistical distribution? Example, all this, I will share this PDF. More real life example is credit scoring, medical diagnosis, marketing campaigns, employee retention, and all that. Okay, so that's logistic distribution. Now, Laplace distribution, if you see double exponential sharp peak signal processing, okay. If you see the practical example here, it is predicting customer behavior, detecting sudden changes in online activity. Okay. Context is in email, in e-commerce or mobile apps, you often track the user behaviors. Because if you see some people, how many clicks, how many purchases, how many session durations, all that. So Laplace, the data is centered, but sharper peaks and heavier tails. I don't want you to understand all this, okay? But I'll give you this PDF. You can go through it. The point that I'm trying to say is, if you want to model it, detect the outlier behaviors, if you want to flag the potential churns, why suddenly the this thing is dropping, the purchase rate is dropping in the retail stores, or promotional offer is working, not working, then you should be able to find out using these distributions. Okay. Okay. Now, uniform distribution, random generation number. This uniform distribution is something which is very familiar to all of us. You are waiting in the bus, for example. Okay, waiting for the bus. The bus will come anytime between 8 o'clock and 8:30. So what we mean that is it's a uniform distribution. It can come at 8:1, 8:2, 8:3, 8:4. So all these timings, whatever that you choose, has equal likely occurrence. Okay, if you heard me in the probability distributions, okay, the event is equally likely. Okay, there is a formula for this, and then this distribution is used when each and every event is equally likely. So the application is simulation, games, probability teaching, testing random access, modeling usage patterns, etc., etc. Okay. And again, I'm going through a little fast because I will share with you this complete PDF, but then I just want to give exposure to these big probability distributions. Okay. Now, again, if we talk about beta distribution, the application that I will share in detail is about. But all of you type PERT in the chat box. If you are in project management, this will be interesting to you. The task time estimation in project management. Okay. There is something called as we are talking here about beta distribution. Beta distribution, okay. And in the project management, optimistic time, most likely time, and pessimistic time, and all that is there. So PERT uses this sort of expected time standard deviations. I'm not going to get into the details of this formula, but you can understand that, okay, it uses certain formula, and then you can use this distribution to find out. It improves planning and risk management. It is bounded, it is flexible, all that you can see. But all I wanted to know is here is a practical day-to-day application of beta distribution is in project management. How do we use this work in exams point of view and all that stuff? Okay, so as and when you have your industry, your applications, then accordingly you should decide what to use. It is like the tool set. Okay, all of you type TS in the chat box. If you buy the set of tools, okay, there can be spanners, screwdrivers, cutting pliers. There can be some key tools like pins, nuts, etc., etc. All the tools are there. Will we use all the tools if there is a problem? Will we use all the tools if there is a problem? All of you type no in the chat box. You don't use all the tools, right? Okay, and similarly, you have gamma, you have triangular, you have Pareto, you have relay. Okay, let me go through just one insurance claim example of gamma distributions. Okay. If you see here, this is a practical day-to-day gamma application is modeling the total time until the specific number of events happen. For example, the real-time situation is, imagine a call center where the incoming calls are handled one by one. Okay. And you are interested in predicting the total time it takes to call 3 customer calls. So this is where gamma distribution is used. So the application is in workflows planning, performance analysis, service level tracking. Okay, how many of you track SLAs? Type SLA in the chat box. if you track SLAs, type SLAs in chat box, service level agreements. Okay, and other gamma distribution applications are insurance, healthcare, and manufacturing. Insurance is modeling claim amounts and timing. Healthcare is time until the patient experiences a certain number of symptoms. And manufacturing is time until the next mission completes multiple cycles. So that's on the gamma distribution front. And now we are going to see the triangular distribution, okay, which is also used in PERT. Okay, triangular distribution is also used in project management. And the same thing in project management, we use optimistic time, pessimistic time, and most likely time. And we use these formulas. Okay, and then it's a common method used in Lean Six Sigma Agile project management methodologies. Okay, some people have a question, right? This lecture is recorded. Yeah, I'm recording this lecture, Koyal. Okay. Koyal is asking whether this lecture is recorded. Okay. I don't know how it matters. Sometimes I wonder people why you go into the detail or whether it is okay live or recorded. It doesn't matter. As long as the knowledge is useful, you can just consume the content, right? It doesn't matter much. Right? How many of you so far found it interesting, useful, valuable, fantastic, awesome? Put it in the chat box. So now what I'm going to do is I'm not going to bore you with this thing, but I'm going to give you this in a platter. Okay. There is also some examples that I've shared here. For example, the binomial distribution. I'm going to give you this PDF where in quality control manufacturing, where the defectives are there, for example, 5% defective, this is used. And Poisson distribution is quite commonly used in the call centers. Okay, it is a call center receives average of 10 calls per minute. The management wants to know the probability of getting 15 calls in a minute to determine staffing needs. Okay, so Poisson comes here. I'll give you this content also. Okay, in geometric distribution, the application is simple. Okay, this is also customer support call. Okay, what is the probability that the first call handled by an agent is a difficult call? Okay, on the fourth try. Okay, look at that complication of that question. All right, so okay, that's interesting, right? So that's where the geometric distributions are used. Okay, and then we have negative binomial distributions. Negative binomial distributions again, as let me close this and this. It's again in the reliability testing fields. In customer support call, especially when analyzing repeat calls until the issue is resolved. Okay, sometimes, same calls happen again and again on the same follow-up happens till it is resolved. How many times it is used? Okay. The company then defines success as fully resolved issue. Only then it is defined as success. Because if I show the presentations, maybe you might not appreciate. And we know Bernoulli, hypergeometric, and this. Okay. Now, that's how we came across non-normal distributions. Okay.